Good morning. Welcome to another episode of Innovation on the Loose, streaming from the DeBakey CV Education studios at Houston Methodist Hospital. And today I'm delighted to have in the studio my special guest, all the way from Johns Hopkins University in Baltimore, Dr. Ali Uneri. Dr. Uneri is currently an assistant research professor of biomedical engineering and is co-director of research and innovation at the Johns Hopkins Carnegie Center for Surgical Innovation. He's here today to discuss image-guided robotics, closing the loop in surgical robotics using interventional imaging. Dr. Uneri, welcome to the show.
Thank you. It's great to be here. Thanks for hosting me. All right. Today I'll present a few example projects to demonstrate how sensing and actuation can come together to create novel approaches for image-guided interventions. So, as you can also appreciate it, I find proximity to the clinic vital for this type of work, and all the research that I'll show was carried out at the Hopkins Hospital in the Carnegie Center for Surgical Innovation, located conveniently between the research buildings in yellow and the surgical suites in cyan. And this is a space that's shared between about 10 core PIs across the schools of medicine and engineering, and I was fortunate to co-direct research activities and day-to-day operations for the past few years. Now, this is historic space, so the first interventional use of X-rays in Dr. Walter Dandy's OR back in 1918s. And since then, advances in imaging, including miniaturization of endoscopes and increased availability of C-arm X-ray systems, have driven the development of novel minimally invasive techniques. Much like imaging, though perhaps more recently, surgical robotics have experienced a similar evolution over the past 2 decades. The Da Vinci system, shown on the left here, was first FDA cleared in 2000, and since then there's been an increasing activity, particularly in the last 5 years, with new devices hitting the market. And similar to interventional imaging, there seems to be a trend toward customized design tailored for specific procedures. And on a personal note, I had the opportunity to contribute to 2 of these systems in the past. On the left is Acrobot, which I worked on as a mechatronics engineer shortly after my master's at Imperial. And Ferdinando from Imperial College actually covered the history of this robot on this channel. So check out that video. Can I say, down in the link below?
Link below.
Link below. And on the right is an eye microsurgery robot I worked on during my first years at Hopkins. The main design has since been repurposed for ENT. Now, robots today are used in a wide array of tasks, and their use is expected to grow by 16% over the next decade. It's hard to generalize their benefits. They're customized, things like, they provide high precision, not necessarily accuracy, and there's increasing kind of levels of task autonomy and promise of remote surgery capabilities that are exciting. I would say the single biggest limitation is their sensing capabilities. So most surgical robots today rely on additional navigational equipment and custom markers. As shown in the case of Excelsius here, this is from the first case at Hopkins after their FDA approval. This device is guided by optical trackers, which limits their ability to track anatomical motion, introduces uncertainty, and ultimately reduces their accuracy. Now, in fact, looking at the next slide, looking at the US spine market, all robots that are mentioned here are guided by tracked markers. But here's another thing to observe. Almost every company here, whether they were originally an imaging or a device company, now owns its own imaging system, navigation solution, and robotic device. And I think investment in these technologies creates novel opportunities and is a sign of things to come for surgical fields beyond spine. So with that, let's dive in. In the 3 examples I'll show, I'll use, each of them will use a different imaging modality. Though they have common characteristics that they support fast acquisition, respect operative time constraints, and are already used as part of the standard of care. So let's start with X-ray. Okay. One of the central themes of my research is extracting 3D information from 2D images. The solutions can seem different depending on the modality or the algorithm used, but the fundamentals are similar. So for example, for X-ray fluoroscopy, it may look like this, where we're trying to find the patient CT in relation to the acquired radiographs. And we can, for example, solve this using iterative optimization, where the 3D image of the patient is iteratively projected in different poses until it matches the acquired images. And more recently, we've been using machine learning to improve various parts of this process, for example, learning task-specific similarity metrics, or replacing this iterative optimization with pose regression, such that all computational heavy lifting is performed during training to yield faster runtimes during surgery. This approach also generalizes to models of arbitrary devices, something that I developed in the latter part of my PhD. And the models can be vendor-provided CAD models, like shown here, or just parametric functions. So in this kind of figure, I model a screw as 2 cylinders, one for the body and one for the polyaxial cap. And combined with the registration of the anatomical model, this allows us to resolve these devices in relation to the patient coordinate frame. And in doing so, we essentially create an X-ray-based navigation system. This does not have rigid body markers, no manual fiducial registration, no dedicated tracking equipment except for the imaging system that's already used, no need for line of sight. So your patient information is your reference marker, and your knowledge of devices are the track tools. So recently we applied this technique in orthopedic trauma, a field that heavily relies on fluoroscopic imaging, where conventional navigation techniques have not been widely adopted. And the task here is to recover specifically the joint function by reducing or bringing together the fibula in alignment with the tibia. And this is a joint that bears the full load of the body. So any malreductions can have significant long-term outcomes, as was shown in clinical studies. And currently the standard of care is to compress these bones together in just 1 degree of freedom and apply certain level of forces. That's the guidance, not a millimeter reduction, just apply 100 to 120 newtons of compression. And as a result, here's what kind of a reduced ankle looks like. And if you need a little more stability, it can have more devices inserted. And here I should add that I have personal stake in this problem, as that image on the upper right is as my left foot. So motivated by that, we set out to kind of provide an image-guided robotic-assisted solution for ankle reduction. And now this is an oversimplified diagram, of course, but the current standard of care requires a surgeon to have a rough plan. Usually that's, for example, matching the ankle to the contralateral side, if that's healthy, or some statistical model in their mind, and apply a reduction, as we established, is just reducing by applying force, and using these 2D images, multiple perspectives to get judge 3D alignment of the bones. Our solution was aimed at quantitatively interpreting the image data to both reduce the uncertainties in the process and enable advanced tools to execute the plan in a more precise manner. So here we start with a 3D image, ideally a cone beam image that's acquired right before reduction. It can also be a CT image before surgery. We use that to automatically generate a plan, and then use routine X-rays, in fact fewer than the surgeon would acquire, just a pair of X-rays to register all the bones and the robot in relation to track the robot as the reduction is happening. So just briefly going over the pieces here, for example, automating planning, we combine image data with population statistics to estimate the likely location of the displaced and or fractured bone. So here, for example, the animation is showing what we call a statistical pose model. And I'm just varying one of the principal components of this model, which shows you how the relational difference between these bones and their shapes can vary. These are all basically healthy variations that the ankle can take place. And then when we bring in the patient image, saying we know what the tibia looks like, the talus looks like, their poses look like, we then ask the question, well, with these information, what's the remaining one? Where should the fibula be placed? And an exact numerical target definition is not only a good thing to have for surgery, but it's also a requirement for devices that need that, such as a robot. And this is kind of our robot design that we came up with, which has a relatively small table-mounted design, an integrated force torque sensor, and limited degrees of freedom to reduce its complexity. And using the available degrees of freedom, we also designed a virtual remote center of motion that allows rotating the fibula about its principal axis, something that's not currently done in surgery with the clamps that are used. And here the center of rotation can be defined per patient based on the imaging data as well. And this is what the system looks like in its latest iteration. So all the guts out, there's no covers on it. This is what the lab equipment looks like, but this is a photo from our cadaver lab studies. Now here, active manipulation is performed on the fibula, while the tibia is held in place with standard X-fix equipment that's used in these kinds of surgeries. And the robot actually doesn't interface the anatomy directly. It holds onto FDA-approved equipment, like the fibular plate that's used. And the parts that are in the X-ray field of view, close to the syndesmosis, were constructed using radiolucent materials so as not to obstruct the view. And when doing manipulation tests, we actually observed significant deviations from the plan due to things like, well, we fixed the tibia, but it can move, or the stability of the joint is different depending on the ligament injury. And even the robot itself is flexing. And that's all great, actually. So here we tell the robot to go someplace, and it's actually doing its best to get there, but things are flexing because these are robots manufactured from cheap materials. But by performing spot checks using fluoroshots and 3D 2D registration, helped account for these deviations and apply course corrections to achieve the target plan. And while I won't be able to cover them, this work also introduced a number of improvements to the registration to handle things like bone collisions, automatically adjust hyperparameters, and reduce outliers, as detailed in our new paper coming out. So the example in the ankle showed how we can use imaging to drive robots and improve their accuracy, and not just their precision. So here in the next part, let's reverse this question. What can robotics do for imaging? And again, I'm motivated by, in this case, imaging of the kidney, but this is a particular project that actually generalizes to other anatomy as well. So the motivation here is that ultrasound is a great portable real-time imaging modality, but we believe its broader use during interventions is hindered by its reliance on skilled operators. So in this project, we asked whether we could automate acquisition of standardized scan planes. Those are planes that capture key anatomic structures. So for example, for the case of kidney, it's this kind of longitudinal cross-section that gives you the characteristic bean shape. And here, trying to get to these standard planes robotically, the benefits are comparable to other similar devices that hold, imaging systems robotically, like the ROSA robotic endoscopy, or even X-rays, attached to robots like the Zigo system. It allows us to get consistent imaging, automatically switch between different views, and free surgeon's hands. And also, you won't need an additional team like a sonographer in the OR. So for our approach here, we use what's called deep reinforcement learning. So this is a method that originally gained traction mostly in robot control, and I see great potential in also robot-assisted imaging like this case. So for those unfamiliar, this is, RL, or reinforcement learning, is about making sequential decisions based on interactions with an environment. So here we adopted the three main components of an RL algorithm for our problem as follows. So first is the interacting with the environment. So this is where, limited image data come into play. You don't have as many labeled ultrasound images available. So we turn to public data sets of CT images. And what we do is we place a virtual ultrasound probe in there, drop it, and then we can navigate it and extract slices that capture the geometry of the ultrasound system that we target, coupled with modern methods for image synthesis that don't try to get an ultrasound image accurately, but just capture the features of the ultrasound image to facilitate training. And then second item is agent. What's our agent? Well, that's the virtual probe that we can move in different ways. So we define 5 degrees of freedom to rotate it in 3 degrees of freedom and translate it in 2 degrees of freedom. It's not 6 degrees of freedom because the probe needs to attach to the skin. And that's great because we're training on CT. We know exactly where the skin is. So we kind of constrain this motion to this surface manifold. And the third is is how do we reward this behavior during training? Well, the common approach here is, look at things like distance from the target plane, how far you are off, and if you're getting close, you can reward it or punish it accordingly. We instead introduce a new reward method that's based on the image data. So here we define it as maximizing the cross-section of the renal pelvis. That is the view we want, as opposed to all the other views you can get. And even though that part is kidney specific, you can totally see how you can construct this reward function for other anatomy. For example, for cardiac applications, there is the 4-chamber view of the heart. You can train it to say, I want equal contribution from 4 chambers in this image, and design your reward function accordingly. And these pieces come together in this Q-learning algorithm. I won't go too much into the detail, but essentially during training, we extract states or these slices from the CT arbitrarily. We synthesize ultrasound images, which go into this trained function that learns how to generate different actions, rotate this way, translate this way, and then we reward or punish its behavior accordingly. And then there are some certain other details, but I would say the most interesting aspect of this reinforcement learning, as opposed to optimizing individual steps, taking the right step, it tries to optimize the long-term gain in getting it. So even if it makes the wrong actions, it can actually turn around and come to the right place. A good example where reinforcement learning was used in solving maze problems. So again, you can go into a right corner, but you can come back and get to the right place. And the results, highlight the potential and also the improved performance we get from our image-based reward. So here on the left, we're looking at reachability. How many times can we reach once we start from random locations around kidney, not necessarily viewing the kidney. And with our image-based reward function, we can get 80% right. And more importantly, looking at the behavior of the trained agent, we can see that it shows an intentional motion towards the target, requiring less than 50 steps, which assuming some robot motion speed and some inference time, it amounts to 20 seconds. You put it around kidney and it gets to the right location in less than 20 seconds. And since then, we've been in the process of completing a full prototype to better understand the limits. This is pure. It was purely software. This is where we hit the hardware and all the challenges that come with it. So this is from our early testing with a hydrogel phantom that we place. We have a robot that's doing force control as it images. And again, what we observe is, just like in our simulation data sets, we observe the same 80% reachability when we apply our algorithm to real images. And just for sanity checking, if we didn't do ultrasound image synthesis during training, there's no chance of generalizing. So that was a critical element in training in CT, which is available data, and then testing the limits in ultrasound. All right, and let's switch on to the last project. So this will show, I would say, a mutually beneficial relation where each robotics and imaging help each other. And the target task here is deep brain stimulation. So this was motivated mostly by emerging DBS techniques and new treatment approaches. And these new treatments are enabled both through identification of novel targets in the brain, as well as our ability to precisely target them. And like in spine surgery, this is a space where robotic solutions are gaining traction, though as you can see from the ROSA endoscopy or the NeuroMate, they're mostly used as simple tool holders. Now, this project has been a large group effort with main goals aiming to provide high quality intraoperative 3D visualization and localizing devices like neuroelectrodes, which is very much like the first project I mentioned. Instead, the devices here are tiny in comparison. Account for deformations, from, for example, things like CSF egress. And then the final piece, carry all that information to augment the endoscopic video scene, the main view that the surgeon looks at. So this talk, I'm just going to cover on that last part. So we have this body of data coming from MR, deformably registered, and our task is to map it, and augment the video scene. So Our general approach here involves reconstructing a 3D surface from the video and registering it to the deformation resolved preoperative context. And the robot here both encode camera poses and provides controlled motion that is free of hand tremor, jerky motions, and motion artifacts. And not unlike the other 3D, 2D problems that I covered, the idea here is to use multiple camera perspective, and this time to triangulate the 3D surface of the ventricles, right? And once again, because this is robotically tracked, we don't have to estimate, we can just use the camera extrinsics from that. And this is, again, much like things like a robotic C-arm does, rotate around the object. And to test our approach, we curated a rich data set of MR images, cone beam scans, and video data. This has been an ongoing clinical study for the past 2 years. And here, because we use numerical information from these imaging systems, we have to calibrate them properly. So before each case, we actually have a student come in and calibrate the endoscope so that we know its distortion parameters, its intrinsic parameters, such that we can apply our methods to it. And this is kind of a 30-page subject test set now. And patient population was mostly hydrocephalus cases, hence the enlarged ventricles. And this is what the process looks like. So here you're seeing, as the video is acquired, surface points on the surface are reconstructed. On the top is kind of an industry standard feature detection called SIFT. That's giving us a sparse point cloud. And on the bottom is our kind of newest trials with a modern machine learning based approach. That is robust, provides robust features that are both reliable and repeatable across different images and conditions. And it has the added benefit that we can train this feature detection on the images of interest, in this case, ventriculoscopy images. And finally, once we train them, this feature detection actually works really fast compared to the others, giving us things like this. So here, basically, this is the same video, this time, again, some random targets here. You can imagine, more task-specific targets visualized. But we can basically bring any structure segmented from the MR in a deformation-corrected manner and visualize in the endoscopic scene to see things behind the visible surface. Seeing the overlay here doesn't do justice. I believe this would be a great application for something like an extended or VR headset. And lately, just as a teaser, we've been comparing these sparse surface reconstructions to dense volume reconstructions to see the extent of how much kind of 3D information we can extract from these images. And we use something called neural radiance fields, which is a type of implicit neural representations. Again, I won't go into the detail, but this is again a problem where, because we know the extrinsics of the camera from the robot, we can pretty much solve the reconstruction problem just like any other 3D reconstruction, back projecting the rays to reconstruct the voxels effectively. And here's kind of our early results from that. Left is again a clinically, an acquired video from our clinical trials. And on the right, we basically reconstructed a 3D image, and we're just tumbling that view around. So what you're looking at on the right is actually a 3D object that you can, for example, reconstruct and have a look around the ventricles, after surgery or for training purposes. So I think there's lots of applications for this, and it's kind of amazing that we can get this from clinical data, no less. All right, so with that, I'd like to conclude. I hope I was able to demonstrate how sensing and actuation can come together. In this case, to combine precise robotic motion with accurate image-based sensing, and how we can use provide 3D navigation using simple 2D imaging. How we can use efficiently use available imaging data in the OR and complement standard of care rather than kind of inventing new workflows. And obviously, I think I try to cater things to robotic assistance, but I believe the technologies that I showed are kind of fundamental or foundational that can enable, once you get that information from interventional imaging, you can enable things like surgical data science to tie it to outcomes, or provide that 3D information rather than on screens, prevent it in like VR and AR headsets. And I'll just end with acknowledging my collaborators, the Carnegie Center, my collaborators at different departments at Hopkins, my funding support from NIH, and our academy industry collaborations. And thank you.
Okay, thank you very much. That was a very insightful and exciting talk. Got a few questions, right? So, at the very beginning, you're talking about the use cases of robotics. I think it was growing by 16% a year or so, right? So, two questions are, what specialities are they really focusing in? What's the emerging specialities, if ever? And are they all surgical assisted robots, or is it more robotics in healthcare in general?
Yeah, I believe that study was focused on surgical robotics. And as for fields, yes, there are different cultures, and not all fields are receptive or their kind of use cases are different. So I would just broadly, for example, based on my observations, I've seen neurosurgery to be kind of at the forefront. Like I see them as more technophiliacs. They're willing to experiment. Whereas certain other disciplines where there are workflow issues, we have seen not just robotics, but even simple optical trackers. You don't see it in their ORs. So I believe opportunities are twofold. In one case, I think there's great growth area in those kinds of disciplines where it's already used. And then spine, for example, is a huge market. But on the other side, I think we can and we will see that we can create new markets by tackling the workflow issues. So often folks, with these technologies focus on patient outcomes, which is of course really important, but you cannot demonstrate patient outcomes if you cannot tackle the workflow challenges. Right? If the surgeon is not willing to, if the OR team is not, taking it in, it is hard to even get to the stage where you demonstrate. And even if the patient outcomes are demonstrated, you don't want people, costing time or pain or uncertainty to the process. So you really need to cater to that. So I believe, big markets like spine or neurosurgery, cranial neurosurgery is definitely going to be pushing this forward. But I see like the smaller markets. Well, actually, even in orthopedic trauma, I showed the example of ankle. But I see especially applying this to long bone fractures or hip fractures, I think is such a great opportunity place if we can tackle the workflow issues.
And workflow, it's not just intraoperative workflow. Are you suggesting it's also the workflow leading up to the surgery itself? So maybe it's, or post-surgery, maybe it's rehab, maybe it's workflow issues in the home, maybe it's actually in the hospital itself.
I would say those are all very relevant, seeing the patient treatment kind of cycle holistically, and even imaging as perioperative imaging. But I was specifically referring here to more of the interventional. I think that's where the real-time constraints are. We can be a little, flexible. For example, run an algorithm for half an hour if it is going to run on preoperative image data. But you cannot afford to do that once the patient's on the table. So the workflow here refers to, especially things like runtime, or things like, do I need to do additional imaging or additional calibration, touch some points with my optical tracker. Those are the hurdles, workflow hurdles that I mentioned. And I think clever use of imaging that's already acquired can provide that solution without adding to the workflow. It's already, the imaging that they would do.
So second question, so moving on to the first kind of examples you gave of your 3D localization models based on 2D intraoperative images. So, they're being run on, I think it was Medtronic's O-arm, right? Is that the imaging system? Yeah. So can that whole workflow, a whole solution be transposed onto another imaging system, or is it specifically for a Medtronic kind of machine?
Well, sometimes the answer is no. In that particular case, it's very much a yes. And in fact, that one is an kind of NIH-funded study, so we're kind of agnostic to the systems. And in this case, we're actually targeting Siemens C-arm, CO spin, which provides both 3D capability and 2D imaging, and it's more like a regular C-arm that's more amenable to orthopedic workflow. But in the lab, we cut corners, we control things, so we can afford to switch the imaging system. So thanks for noticing. That's right. Yeah.
So once you're getting all this preclinical data, research to showing that it's working. So how do you then transition into the clinic? And is it a software approach that you're really implementing? Do you work with the FDA? Maybe comment on that about how you actually translate it into the clinic.
Right. Yeah. So that's always a challenge. So there are different tricks we can do. We oftentimes do what's called retrospective studies. So we will have IRB data access to clinical data. Sometimes it will not be retrospective, but we will retrospectively analyze it. So we work with our surgeon collaborators to get the right images, to have somebody in the OR, somebody in technical background, kind of noting what images are required, what the situation is. So control data collection, but then we will go ahead and simulate what things would be if, for example, a robot was used. We actually did that for some of the data in the neuroendoscopic case. We didn't have the robot holding the neuroendoscope. What we did was to use a time-intensive process to estimate the camera extrinsics that a robot would provide offline, something that we cannot afford to do during surgery. But in doing so, we were able to get close to, like, if a robot were to acquire, this is the type of data we would get. So those are the tricks. But once you kind of want to test, like, we want to bring this ankle robot into a clinical trial, and it's not a clinical trial so much as a pilot study of 10 patients. So that requires, a proper approval. So the main channels we go for is the FDA's IDE program, and we work with them to make sure everything's up to spec. So that plus the IRBs, especially for kind of a new system like this. Again, it's not a traditional 1,000 case clinical study, but I would say pilot feasibility study.
Got it. And you mentioned this a couple of times, but can you comment on the use of extended reality and spatial computing technology in this field of image-guided navigation and robotics?
Right. So the way I see it is, all my career I've been kind of trying to extract this 3D data, and it's been kind of sad to see it just projected onto this 2D TV screen. On top of that, you present it, and we had clinical trials where we present another monitor with our output, and the surgeon has to kind of look up to it. It just doesn't have, it's hard to convey that. You scroll slices, and so to me, it's such a great output source once you have this 3D information that marries, like population statistics or preoperative information. It's such an ideal platform, and certain disciplines like orthopedic surgery is really interested in seeing that. For example, you're aligning bones and you want to see your plan or trajectories of like the principal axes of the fractured pieces. Here's how I will position it with robotics. I would say if you need precise controlled forces, maybe scale forces like microsurgery, then robotics provides something that is beyond your abilities, beyond what you can do with your hands. And that's what laparoscopic surgery, how it transitioned into robotic laparoscopic surgery. But for other cases where you do not need that level of precision, I think AR is a cheaper or achievable target, especially for things like point of care treatment, where you cannot have a robot at either an ambulance or some outpatient center. But it will be so easy to deploy these VR headsets if you can power them with smart imaging and image analysis to bring the right content.
Couple more questions. So obviously The integration of AI into all this, how important is that and how game changing? Maybe just comment on AI.
Yes. Oh, this is such an exciting time to do this research. Back when I was kind of presenting this kind of numerical optimization techniques, it's kind of standard question has been like, okay, it's great, but what's the runtime? This community, it's so important, because if you have this method, it's working, but it takes, half an hour. But we always knew that computers get faster, we can run it faster in the near future. We just didn't know the nature of the fast. So one of the biggest game-changing things of AI has been the runtime. I mean, even things like 3D deformable image registration, when it came about, the AI did not provide higher accuracy. In fact, it was slight lower accuracy. But man, doing all that optimization during training time, you can run a deformable registration in a split of a second. That's a game changer, and it applies to many of the tools, techniques that I showed. Is being able to run these. I cannot imagine asking these questions or tackling these problems with technology from even 10 years ago. So that's part one. Second part is it's such a great information extractor. Again, we are not in the intervention setting. I would say we're not working with pretty images, and some modalities are worse than others. Well, there are trade-offs. Like you get really nice high spatial resolution with ultrasound, but image quality is not pretty to look at. But they are great information, measurement devices. So whereas previously it was a hassle just segmenting ultrasound images, now we can extract features from it to carry out something like registration. I haven't mentioned it, but we actually have a project where we are using ultrasound imaging to register the spine. Again, it's spine image, bone imaging with ultrasound. There are more artifacts than signal. But I say this, one man's noise or one man's artifact is another man's signal. So we've been using things like bone shadow information to predict where the bone is to carry out the registration. So it's been an incredible information extraction technique. And I'll say one more advantage that's been a game changer is much of the time interventional imaging and these techniques, it takes multiple different modalities. You have some preoperative modality, or even during operation, you got 3D or 2D, ultrasound or X-ray. So, for example, the ability to synthesize images from one modality to the other. Now, I should clarify, you don't really synthesize measurements. You can't, measure ultrasound acoustic impedance from Hounsfield units. But you can correlate it enough to reduce a complex multimodality, for example, image registration problem, to a monomodality registration problem. So now we can, previously we were cooking up fancy similarity metrics to run MR to CT registration. Now we're saying, I'm going to synthesize a bone image from MR, a bone image from CT, and now it's trivial to register them. Wow. So that that has been a game changer in many of my techniques, whether it's training my ultrasound approach in CT, or again, registering CT to MR. That has been a game changer. Image synthesis has, again, been computationally intensive and very ad hoc, very domain dependent in the past.
So it kind of ties into my last question there. I think you probably already answered it, but it was regarding technology limitations and bottlenecks, right? So where I'm going with that is like the computer industry, right? So you make computer chips. The technology bottlenecks there are, it's got to be based on silicon chip kind of technology. You only get so small. So they looked at quantum computing, carbon nanotube chips, etc., right?
Yeah.
So what are the technology bottlenecks in image-guided navigation and robotics? But it sounds like whatever they are, AI is kind of overcoming them, right?
Yeah. So things like, and again, when Axel Krieger was on the show, he also mentioned it, that robotics, like the mechanical design, we got a pretty good handle on that. We know how to manufacture these systems. It's not about that. I believe sensing is a limitation, but AI is allowing us to do so much more with it. But here's a resource limitation. We always had difficulty, working with data, and now these techniques are even more data hungry. finding creative ways around that through simulated, in silico training or just transfer learning of different things. But there's so much. Well, it's not ideal, right? One of the single biggest problems with these AI techniques is its generalizability. So, there is kind of the theoretical aspect of how we manage that. For example, what we've been doing with that is, rather than try to understand what the AI is doing, like introspection, it's tough. We've been going the route of quantifying uncertainty. So quantifying things like epistemic analytics, uncertainty associated with the algorithm's output, at least to warn the surgeon that it's not sure about this prediction, right? So that's one aspect. But all of that, especially, epistemic uncertainty, would be reduced if we had access to more data, which, again, I think we need, dedicated, beyond the single discipline efforts to get data curation, data anonymization, data safety in a manner that we can more efficiently use it, especially for smaller scale problems, clinical problems. That resource is it's a big bottleneck.
So when you say data, can you be more specific? Do you mean like DICOM imaging sets, like CT, MRI, anything else? Yes. So because a lot of my research is image-based, there's definitely imaging data limitations. That even when you see things online, like publicly shared, the quality or how it is acquired. So when we do IRB studies, when we go into the clinic, we are present there. We know what is acquired because a lot of that is not like DICOM in interventional imaging. I don't know if you haven't looked at it. The fields are not nearly as enforced as in diagnostic. You don't know how the patient was positioned. You don't know what protocols were used. So that's one aspect of it. The other aspect are things like, well, if you're thinking about supervised learning, you got to have some labels. So again, this is a place where, we're looking into novel approaches that avoid having to have, for example, people segmenting things day and night, which introduces inaccuracies there as well. So that's why, for example, we don't have ultrasound labeled data set. That's very difficult. That's why we go to CT and try to generalize it to ultrasound. That's a workaround to the limitation of labeled data set, at least when it comes to supervised learning. So there's also kind of exciting development in unsupervised training approaches, which kind of get around that in a more kind of elegant way when they work. Got it.
Yeah.
All right, well, on that note, I'd just like to say thank you to our audience for watching. Obviously, don't forget to subscribe. There'll be more details in the link below. And Dr. Uneri, thank you very much for joining me in the studio. Hope to see you again.
Thank you. It's been my pleasure.
Thank you all.